Linear Algebra for Data Science. In this course, you will build a deep understanding of linear algebra, starting from the basics and going step by step to more advanced topics. You will also see how abstract concepts are applied to real data science problems. Chapter 10. Orthogonal Projection. Section 1. Orthogonal Vectors and Projections. This section covers what is projection, the concept of orthogonality and why it is important in understanding projection, how we can apply projection and the concept of orthogonality to data science. Let's start with definition of orthogonality. Two vectors u and v in Rn are said to be orthogonal if their inner product is zero. Orthogonality means that the vectors are perpendicular to each other in Euclidean space. For example, in R2 or R3, orthogonal vectors form a 90-degree angle. Let's see some examples of orthogonal vectors. Let's start with a two-dimensional example. Consider vectors u and v in R2. As calculated by this expression, their inner product is zero. Since the inner product of u and v equals 0, the vectors u and v are orthogonal. Next, let's see an example of a three-dimensional example. Consider vectors u and v in R3. As calculated by this expression, their inner product is 1. Since the inner product of u and v is not 0, the vectors u and v are not orthogonal. Orthogonal vectors have several important properties that make them useful in various applications. 1. Zero inner product. First, as defined, orthogonal vectors always have an inner product of 0, indicating they are perpendicular. 2. Orthogonal set. Second, a set of vectors is orthogonal if every pair of distinct vectors in the set is orthogonal. Besides, if each vector is a unit vector, the set is called an orthonormal set. 3. Simplified calculations. Orthogonal vectors simplify many calculations in linear algebra. For example, when computing projections or solving systems of linear equations, orthogonal bases reduce computational complexity. A projection of a vector onto another vector or subspace is essentially the shadow or footprint of the vector on that subspace. Projections are widely used in data science to reduce dimensionality, simplify models, and find relationships among data points. The projection of u onto v can be visualized as the shadow of u along the direction of v. If we have a vector u in space, its projection onto another vector v is the closest point to u that lies along the line defined by v. If you think of u as a point in space, it is generally not on the line defined by v. To find a point on that line that is nearest to u, we drop a perpendicular from the tip of u onto the line defined by v. The point where this perpendicular meets the line is the projection of u onto v. The projection of vector u onto another vector v is calculated by this formula. To project a vector u onto another vector v, we calculate how much of u lies in the direction of v. The formula for the projection of u onto v is given by this formula. Let's explore what this formula means in detail. Here, we want to find the projection of a vector u onto another vector v. This projection is a new vector that meets the following two criteria. First, the new vector points in the same direction as v. Second, it represents the shadow of u along v. The key idea behind the formula is that the projection is essentially the scaled version of v, where the scaling factor depends on how much u aligns with v. Let's understand how this works step by step. Step 1. How much does u align with v? The inner product of u and v tells us how much u and v are aligned. If the angle between them is 0 degree, they are perfectly aligned, and the inner product uv is maximized. If the angle is 90 degree, they are perpendicular, and the inner product uv equals 0, meaning no alignment. Thus, the inner product of u and v measures how much the vector u points in the same direction as the vector v. Step 2. Scaling v. To get the projection, we need to scale v so it represents only the part of u that aligns with it. Besides, we need to ensure the scaled v has the correct size. The scaling factor can be calculated by this formula. The numerator is the inner product of vector u and vector v, which represents how much u aligns with v. The denominator represents the size of vector v squared, used to adjust for v's length. The inner product of two vectors depends on the sizes of the vectors and their alignment. To remove the effect of the size of vector v and focus only on the directional alignment, we divide by the squared magnitude of vector v. Step 3. The formula. Now, the projection can be expressed by this formula. This formula ensures that the projection is in the same direction as v. That is, it is a multiple of v. This formula also ensures that the magnitude is proportional to how much u aligns with v. Let's see a simple example of projection. Consider two vectors u and v in R2. First, calculate the inner product of u and v and v. Now, using the formula, compute the projection of u onto v. Now, we can obtain the projection of u onto v. The concept of projection can be extended to projecting a vector onto a subspace spanned by a set of vectors. This is often useful in applications like principal component analysis, where data points are projected onto a lower dimensional subspace to simplify analysis and reduce noise. To project a vector u onto a subspace spanned by an orthogonal set of vectors, we sum the projections of u onto each vector. Let's see a simple example. Consider a vector u and a subspace spanned by vectors v1 and v2 in R3. To project u onto the subspace spanned by v1 and v2, we compute the projection onto v1, the projection onto v2, and then sum the projections. First, compute the projection onto v1 by this expression. Next, compute the projection onto v2 by this expression. Now, sum the projections. So, the projection of u onto the subspace spanned by v1 and v2 is 3, 4, 0. The formula of the projection onto a subspace holds only when the set of vectors are orthogonal each other. If the vectors in the set are orthogonal, The projection of u onto one vector does not interfere with the projection onto another vector. This means that the contributions from each vector to the overall projection can be added independently. Besides, when the vectors are orthogonal, their dot products are zero. This ensures that the projection calculation for one vector doesn't overlap with the others, allowing the sum of individual projections to correctly represent the projection onto the entire subspace. If the vectors are not orthogonal, the projections onto Vi and Vj are not independent. The sum of these individual projections will not be equivalent to the projection onto the span of all the vectors. In this case, you would need a more general method like the Gram-Schmidt process or solving a system of equations to compute the projection onto the subspace. If the vectors are not orthogonal, the projections onto Vi and Vj are not independent. The sum of these individual projections will not be equivalent to the projection onto the span of all the vectors. In this case, you will need a more general method like the Gram-Schmidt process or solving a system of equations to compute the projection onto the subspace. The Gram-Schmidt process will be covered in the following lectures. Orthogonal vectors and projections are applied to various machine learning algorithms and data science techniques such as regression analysis and principal component analysis. In regression analysis, orthogonal projections help minimize the sum of squared errors. For example, in linear regression, the best fit line is found by projecting data points onto the line, minimizing the perpendicular distances from the points to the line. Principal component analysis is a dimensionality reduction technique that projects data onto a lower dimensional subspace formed by the principal components, which are orthogonal to each other. This orthogonal projection maximizes variance and minimizes redundancy, simplifying data analysis and visualization. Orthogonal vectors and projections are useful tools in linear algebra and have numerous applications in data science. Orthogonal vectors simplify many computations, making algorithms more efficient and robust. Projections enables us to reduce dimensions, focus on important features, and improve data analysis and model performance. Understanding this concept is essential for building effective machine learning models and solving complex problems. Thank you for watching. Please thumbs up and subscribe to my channel.